Have you ever stood outside at night and looked up at the stars? It seems like all the stars are sprinkled across a giant dome above us. But have you ever wondered where exactly are those stars located in the sky? And how do we describe their positions from Earth? What if we imagine the entire sky as a big hollow sphere surrounding our planet with stars fixed on its inner surface? That's the idea behind the celestial sphere. A celestial sphere is an imaginary sphere of an extremely large radius with Earth at its center, on which all celestial objects like stars, planets, and the sun appear to lie and move. There are few terms related to celestial sphere. Zenith, the point directly above your head. Nadir, the point directly below your feet. Celestial poles, the extension of Earth's north and south poles onto the celestial plane. This is called the north celestial pole and this one is called the south celestial pole. Celestial equator, the projection of Earth's equator onto the celestial sphere. Horizon, the boundary line where the sky seems to meet the Earth. Ecliptic, it is an imaginary plane containing the Earth orbit around the Sun. It is tilted at an angle of 23.4 degree with the north celestial pole because of the tilt of the Earth. But how do we read the position of a star? There are two ways. One is the equatorial coordinate system and the second one is the horizontal coordinate system. Like we are having latitude and longitude on Earth, similarly we have declination analogous to latitude and right ascension analogous to longitude in the equatorial coordinate system on celestial sphere, with celestial equator at 0 degree, the north celestial pole at plus 90 degree and the south celestial pole at minus 90 degree. The right ascension measures object's position eastwards along the celestial equator starting from the vernal equinox. Vernal equinox, it is the point where the ecliptic intersects the celestial sphere. This concept is already introduced in the previous video. Right ascension is expressed in hours, minutes, and seconds. So, 24 hours is a 360-degree full circle and 1 hour is equal to 15 degree. So if a star is with right ascension 5 hours 30 minutes, it is 82.5 degree east with the vernal equinox. Here you can have a look of the position of a star in the equatorial coordinate system, the declination and the right ascension measured from the vernal equinox. In the horizontal coordinate system, we use the terms azimuth and altitude. Azimuth is the angle between the north direction and the point on the horizon directly below the celestial object, measured clockwise from 0 degree to 360 degree. 0 degree is north, 90 degree is east, 180 degree is south, and 270 degree is west. Example, if a star has an azimuth of 135 degree, it is located southeast from the observer's point of view. Azimuth is always paired with altitude, the angle above the horizon. Here are the few right ascension and declination of some famous stars given, like Sirius is having the right ascension of 6 hours 45 minutes and declination at minus 16 degree 43 minutes. But is it sufficient only to know the right ascension and the declination or the azimuth and the altitude of a star to view it from a telescope? No, because the Earth rotates once every 24 hours from west to east. This causes the celestial sphere to appear to rotate from east to west around us. And because of this rotation, different right ascension and declination positions come into view throughout the night. Although the position of the right ascension and declination are tied to the background stars and not Earth, so they do not change due to the rotation of Earth. But what changes is the local sky. This is described by the local sidereal time. It tells you which right ascension is on the local meridian at any moment. So as the Earth rotates, the right ascension value directly overheads changes through day and night. Note down your position coordinates, that is the longitude and the latitude from the world map, and also your local standard time. Like for India, it is IST, and convert it into GMT. You can calculate the local sidereal time from this website. Like if you are facing south, curving from the south point on the horizon up to the zenith is an imaginary line in the sky known as your meridian. Everything in the left of the sky, that is from the east, is rising, and on the west it is setting because of the east-west rotation. Thus, knowing one's latitude and longitude of their place, it will help in finding the meridian for declination and the celestial equator for the right ascension. Here you can see the meridian. It is marked as 0 degree, 15 degree, 30 degree, 45 degree, and it will go up to 90 degree till north celestial pole, and downward direction also to minus 90 degree till south celestial pole. The right ascension will be marked as 0 hour, 1 hour, 2 hour, like this for 24 hours for a full circle. Here you can see the position of the right ascension is changing throughout the day, but the declination remains the same. Sidereal day and a solar day. A sidereal day is the time it takes for the Earth to rotate relative to a star. It is 23 hours 56 minutes. And a solar day is of 24 hours. That is the time taken by the sun to return to the same position in the sky. So a sidereal day is always 4 minutes ahead of the solar day. It affects on sliding our star chart to the right by 4 minutes of right ascension per day, in addition to the complete rotation of 24 hours of right ascension it makes. These two factors combine so the right ascension of everything up there changes not only every hour but every day they slide a little further to the west. Position of the ecliptic also influences the view of the night sky. When the Earth's tilt causes the northern hemisphere to be tipped towards the sun's path, the ecliptic, and the sun can be found high in the daytime sky. And when the Earth tilt causes the northern hemisphere to be tipped away from the sun, the ecliptic can be found low in the daytime sky. During winter, ecliptic is the highest in the nighttime sky, and it makes easier to see other planets and asteroids in the winter time. Except for Pluto, rest all of the planets lie close to the ecliptic. This is due to the revolution of Earth around the sun and the axial tilt. You can see the position of the ecliptic changes throughout the year. One more factor affects the direction in the sky, that is to which the North Pole points, and that is the precession of Earth. But it happens in a very long run, and it is already explained in the previous video. Set the telescope to view the stars. The equatorial mount. It is a setup so that the entire mechanism, including the telescope and the counterweights, rotate around the celestial pole just as the sky does. The mount only has to move the telescope in the right ascension as the time goes by to track objects rising in the east and setting in the west. This means only one motor is required, although a declination motor is often supplied as well to make pointing the telescope to a new object easier. If you point the telescope to another object, different RA and declination, the process continues again. In the ordinary telescope, that is the Dobsonian telescope, a simple tripod mount for a refractor or reflector is there. Here you will have to manually keep the telescope on the object of interest. This involves manually moving the telescope up and west as the object rises and down and west as the object sets. This type of mounting is not recommended for astrophotography because it is very difficult to continuously aim the telescope precisely. However, it is the least expensive mounting and is still very good for visual observing and making drawings or sketches of the celestial objects. The view through a telescope is often inverted, sometimes just left-right, but also maybe north-south as well. Telescopes without flat mirrors in the path of the optics invert both horizontally and vertically. Newtonians, Dobsonians, and other configuration with one flat mirror in the optical path use the mirror to correct one direction but not two. A special prism corrector may be used with telescopes to correct for both directions, making them useful for terrestrial observations as well. There is no up or down in outer space. However, these reversed views can make it hard to find objects by looking through the eyepiece and moving the telescope. You will find that movement in one direction causes the image to shift in another direction. Here you can see the setting scales for declination and the right ascension. These are called the setting circles. Here, this can measure in arc minutes. These are the star maps. They are the printable maps you can download. Here you can see the right ascension and the declination for Hercules star. Thank you.